Next, we go to example 3. A spherical capacitor consists of conductor plate at R equal to 10 cm and R equal to 30 cm. The outer conductor plate is said to be earth, while the potential for inner conductor is 100 volt. Given that the relative permittivity for the electric, which is between conductor, is changed with R, in which epsilon R equal to 2.5. Find first the potential in dielectric, second electric field intensity in dielectric, third total charge on the inner plate of sphere, fourth is capacitance, and lastly total bounded charge. So for the solutions, this is a case. So we have the spherical, let's say spherical capacitor. So we connect one of the surface, which is we take the inner surface to be connected to 100 volt, while another surface, when R equal to 30 cm, we connect to the negative part. So one is 100 volt, another one is 0 volt. So the potential between A and B is 100 volt. So we set RA to be 10 cm equal to 0.1 meter, RB equal to 30 cm equal to 0.3 meters. And we use the spherical coordinate. Right, so refer to the spherical coordinate for Laplacian. So we take only the variable R because our capacitor in change with R. So we have to solve this part. Okay, when you solve this part, we got VR equal to negative C1 over R plus C2. And we have to find out what is the variable C1 and the variable C2. We have to apply the boundary conditions when R equal to 30 cm or 0.3 meters. So we put inside the formula, we got V 0.3 equal to negative C1 divided by 0.3 plus C2 is equal to 0. From here, you got C2 is equal to C1 divided by 0.3. When R equal to 10 cm or 0.1 meter, V 0.1 equal to negative C1 over 0.1 plus, this is C2. C2 equal to C1 divided by 0.3 equal to 100. Solving this, we got C1 is equal to minus 15. So we put inside the original formulas. We got later on the VR equal to 15 divided by R minus 50 volt. This is the general equation for VR between the two plates. Next, the electric field intensity, we can use the gradient for spherical coordinate. So again, we only interested in R components. So later on, when we solve the gradient, you got E equal to 15 divided by R square in the direction of R volt per meter. Next, the charge density. The charge density at R equal to 10 cm or 0.1 meter is equal to dN, equal to epsilon naught En, equal to epsilon naught E dot N component. Basically, we have to remember that the D is always the same outside and inside the dielectric. The only difference is the E component. So basically, we have two solutions, and the solution will be the same. Okay, the end result will be the same. So for example, here I take the E is E outside dielectric. Okay, the E is outside dielectric is equal to D divided by epsilon naught, where D is equal to epsilon E in, because D is the same. So epsilon E in inside the dielectric, and then you got what is the E out. And then we can find what is the rho S. Rho S equal to dN is equal to epsilon naught E out, and this is the final solution. If you use the E inside the dielectric, you also can, because here we only need to know what is the D. Okay, the dn. So the D is basically equal to epsilon E. We can use the E inside. So the final answer will be the same. So add the 1. So the charge at R equal to A, QA equal to rho SA SA. So the S here is the surface of using the spherical coordinate, which is 4 pi r square. So we can cancel out the r component, and later on you got QA equal to 150 pi epsilon naught coulomb. Next, what is the capacitor? The capacitor is equal to charge divided by potential. So the charge QA equal to 150 pi epsilon naught. You already calculate here. And divide the potential between A and B is 100 volt. So you got the capacitor equal to 1 over 1.5 pi epsilon naught farad. And lastly, we want to find, again, what is the equations? We want to find total bounded charge. Total bounded charge is basically inside the dielectric, so we need to find the polarizations. So we have to find the bound surface charge here. The rho SV equal to polarization dot product with a normal component to the surface, where the polarization equal to D minus epsilon naught E, where this E is E inside the dielectric. Okay, and the D is equal to epsilon E. Okay, so D equal to 2.5 epsilon naught 15 divided by R square divided by R. So this is epsilon inside the electric and E inside the electric. Or you can use the E, the epsilon outside the electric and the E outside the electric. So the D will be the same lah. And this is, when solving this, you got equal to 37.5 epsilon naught divided by R square R. This is D. Therefore, the polarization equal to 37.5 epsilon naught divided by R square in direction of R minus epsilon naught 15 divided by R square in direction of R. So this is the final solution for your polarizations. Right, after we obtain the polarization, we can later on determine the bound surface charge at the surface of our dielectric material between A and B. So we can determine the rho SB at R equal to 0.1 meters and rho SB when R equal to 0.3 meters. So it can be determined by using the polarization dot product with the normal vector normal to the surface. Let's say when rho SB at R equal to 0.1 meter, which is at the inner surface of your sphere, so the normal vector will facing inward to the sphere. That means the normal vector become negative R. When R equal to 30 cm or 0.3 meters, so the normal vector basically facing out of the surface. Okay, this is positive R. So solving these two, we got negative 2250 epsilon naught coulomb per meter square when R equal to 0.1, and another one is 250 epsilon naught coulomb per meter square. Next, having these two rho SB, you can later on determine the total bounded charge, which is QSB at R equal to 0.1 meter and QSB when R equal to 0.3 meters. So we use the rho SB as A and rho SB as B. So basically, I will not put the value for R because later on the R can be cancelled out. So solving this, you got the final answer to be negative 90 pi epsilon naught and 90 pi epsilon naught coulomb. So you can see that the magnitude of the charge will be the same, but one charge is negative, another one is positive, right?